This question asks you to identify which statements about the Sklearn, utils, extmath, fastlogdet function are accurate. This function is used for calculating the logarithm of the determinant of a matrix, a common operation in statistics and machine learning. Let's carefully analyze each statement. This statement claims that fast_logdet is universally faster. However, the speed comparison depends on factors like matrix size and the specific hardware, software involved. While fast_logdet is designed for speed, it's not guaranteed to be faster in every single scenario. Think of it like comparing two different routes to a destination. One is generally quicker, but traffic or unexpected delays could change that. This is correct. Fast_logdet cleverly employs the Sklearn decomposition method. This is a specialized way to break down a matrix that's particularly useful for positive definite matrices. It helps make the calculations more reliable and significantly faster than the naive approach. Think of it as a shortcut through a complex calculation. This is false. A singular matrix has a determinant of 0. The logarithm of 0 is undefined. Negative infinity. Thus, fast_logdet, which aims for numerical stability and efficiency, can't directly handle such cases. It's designed for matrices that are well-behaved numerically. This is true. The Sklearn decomposition works best, and most efficiently, with positive semi-definite matrices, where all eigenvalues are non-negative. While it might work on other matrices, fast_logdet is optimized and designed primarily for this type of large matrix. It's like having the right tool for the right job. A hammer is great for nails, but not so much for screws. This statement is true. The fastlogdet function uses Sklearn decomposition, which works best, and is most efficient, with positive semi-definite matrices. These are matrices that are symmetric and have all non-negative eigenvalues. Thinking of it another way, they represent a type of quadratic form that is always non-negative. While fastlogdet might technically work on other types of matrices, it's designed and optimized for this specific kind, ensuring both speed and numerical stability. That's why it's considered primarily intended for them. This line introduces the topic of the quiz. Understanding the fast_logdet function within the scikit-learn library. It sets the stage for the questions that follow, focusing on a specific function within a popular machine learning library. This function is used for calculating the logarithm of a matrix determinant, a key concept in various statistical and machine learning applications. This line presents the core quiz question. The quiz will evaluate your understanding of the extmath, fast_logdet function's capabilities and limitations. The question asks to identify true statements from a list of options related to the behavior and performance characteristics of the function. Option A claims that fast_logdet is always faster than a naive approach which involves directly computing the determinant and then applying the logarithm. Is this always true? The question prompts us to consider scenarios where the efficiency might vary due to factors like matrix size, structure, and the underlying linear algebra implementation. Option B suggests that fast_logdet utilizes the Sklearn decomposition. The Sklearn decomposition is a method to decompose a positive definite matrix into a product of a lower triangular matrix and its transpose. This is a computationally efficient and numerically stable method for computing determinants of such matrices. Option C examines whether fast_logdet can handle singular matrices with a determinant of 0. Can this function gracefully handle such cases, or does it have limitations? The question explores the robustness of the function, its ability to address potential numerical challenges associated with ill-conditioned input. Option D proposes that fast_logdet is best suited for large, positive semi-definite matrices. Positive semi-definite matrices are symmetric matrices where all eigenvalues are non-negative. The question targets the intended application domain of the function, considering its efficiency and stability characteristics with different matrix types. This line indicates that multiple options from the preceding list might be correct answers. Think carefully, it is not a single-choice question. The instruction requires careful consideration and evaluation of each statement's validity. Let's explore the statements one by one to understand the scikit-learn's extmath fast_logdet function better. It's all about efficiently calculating the logarithm of the determinant of a matrix. Think of the determinant as a single number summarizing some key properties of the matrix, and the logarithm just helps with scaling and numerical stability. This function is particularly useful when dealing with covariance matrices, which often arise in statistics and machine learning. We'll look at each statement carefully, considering its implications and whether it aligns with the known behavior of fast_logdet. This statement is a bit too strong. While fast_logdet is designed for speed and efficiency, its performance isn't guaranteed to be faster than a naive approach in every single scenario. The actual speed depends on many factors like the size of the matrix, its properties, is it sparse? Is it well-conditioned, and the underlying linear algebra libraries used by scikit-learn. Sometimes, a direct calculation might be surprisingly quick, especially for small matrices. This statement is true. Fast_logdet cleverly uses Cholesky decomposition, a powerful technique for factoring a positive definite matrix. It's like a sophisticated way of breaking down a complex matrix into simpler parts, which greatly simplifies the calculation of its determinant. This approach also brings increased numerical stability, meaning it's less prone to rounding errors during computation, which is essential when dealing with floating point numbers. This statement is false. A singular matrix has a determinant of 0. Taking the logarithm of 0 leads to negative infinity. The fast_logdet function is not designed to handle such cases gracefully. It is optimized for well-behaved matrices and will likely raise an error or produce an undefined result if presented with a singular matrix. This is true. Cholesky decomposition, the backbone of fast_logdet, works particularly well with positive semi-definite matrices where all eigenvalues are non-negative. Large matrices of this type are common in machine learning, especially in covariance calculations. So, the function is tailored to this scenario to leverage the efficiency of Cholesky decomposition, giving both speed and numerical stability. This question is the core of the quiz. It asks you to assess your understanding of the scikitlearn function fastlogdet, specifically what it does, its limitations, and the maths behind it. It's all about choosing the correct statements about how the function works. This presents the multiple-choice quiz problem. Each statement needs careful evaluation based on your knowledge of fastlogdet. It's a test of your understanding, not your coding skills. This statement claims that fastlogdet is always faster. We need to consider if this is universally true, or whether there might be exceptions. This statement suggests fastlogdet uses a specific mathematical technique called Cholesky decomposition. We should check if this is correct and if it contributes to the function's speed and reliability. This statement says fastlogdet works on singular matrices. We need to understand what singular matrices are and if the function is designed to handle them. This statement gives information about what types of matrices fastlogdet is best suited for. We need to know what positive semi-definite means in this context. The statement is about the function's purpose.